Okay, so what I plan to do in this video is show you how to run through a hypothesis testing question for the population mean using the t distribution. I believe this example is the t distribution problem. The process for using the normal distribution in z-scores would be exactly the same thing. So what I've done is I've created, this is your template, and it's a skeleton version, so I could, modify it right now. The template that you print out looks a little nicer. It has lines and everything where you could fill in the blanks. Remember, whenever you do one of these questions, you want to print one of these templates out because what it does is it kind of organizes your thoughts. So let's give a look here. This example is on Twitter usage. It says on Twitter, the average number of tweets per day is known to be 2.86, okay, for persons that have 500 or fewer followers. Apparently, the more people that follow you, I guess the more important you feel, and you tend to tweet more often. All right, so for 500 or fewer, there's the average is 2.86. So there's your null hypothesis, obviously. Remember, the null hypothesis is a statement about a population parameter, like mu, that's known to be true. A local sociologist feels that this average is too low. All right, so that statement too low. If you think something's too low, obviously you think, in fact, the real number is higher than that, right? So there's your alternative hypothesis. So for our hypotheses here, the null hypothesis, the population mean equals 2.86. And then the alternative to that, this sociologist feels it is greater than 2.86. All right, so those are your null and alternative hypotheses. So remember, the null hypothesis is assumed to be true. The alternative hypothesis is a suspicion. It's like a gut feeling, and you're trying to, this is what you're going to use to oppose this null hypothesis. So, let's keep reading here. She randomly samples 100 people. Okay, so there's your sample size, and finds an average of 3.05 tweets per day, with a sample standard deviation of 0.66. All right, so I'm going to actually highlight that. I'll bold it a little bit, put it in red. That thing right there, that's the key, because the sample standard deviation, that's what lets you know you're using the t distribution, remember. If you're given the population standard deviation, you use the normal distribution. And if you're given the sample standard deviation, as in this case, you'll use the t distribution. Okay, based on this information, can we agree with the sociologist at a 1% alpha? All right, so we got our hypotheses. So we stated that. All right, so let's go ahead and read down the left-hand side of this template and start filling in the little bits and pieces. And the sample size, well, they give us that. It's 100 people. So she grabbed 100 people there. Those 100 people produced an average. Now remember, that average is a sample average. Don't forget, this is an average too, right? This is the population mean, 2.86. You're trying to oppose this. She grabs 100 people, finds the average. Her average was 3.05, which, by the way, notice, is in fact bigger than 2.86. So maybe, her suspicion is actually correct. We don't know. We have to first do the test, right? All right, so now it says sigma or S. So this template is, it works for both the t distribution and the normal distribution. So when you're working with this, you should, circle, or I don't have the ability to circle here, so I'll just highlight. We got the sample standard deviation, and it gave it to us. It's 0.66. So 0.66. All right, so here's a big question here. Distribution with a question mark. All right, so obviously we're going to use the t distribution because we have the sample standard deviation. If the question gave us the population standard deviation, then we'd be using the normal distribution. All right, so I'll say t distribution with degrees of freedom equal to, now remember, the degrees of freedom is always equal to n minus 1. All right, there's 100 pieces of data, so there's n. So you take one away from that, and you get 99 degrees of freedom. All right, alpha was given to us as 0.01, which means 99% confidence. Okay, so now we have our z. It says z or t. What do you got? Well, obviously we have a t-score, so let me highlight the t. Why is it a t-score? Well, because we have a sample standard deviation. So this kind of goes right in order. You pick your standard deviation. That's given in the question. That's going to dictate whether you're using t or z. All right, this is a t distribution. And then you need your critical z-score or t-score that you're going to pop in over here. Now I have it labeled as z, as you can see over here. I'll have to fix that. Let me change that. That's going to say t sub c. All right, so a couple things we should note. First of all, if alpha is 0.01, which is 0.01, let me pop that right over here somewhere. There's alpha. That's that little shaded region right there. Then the confidence level is 99%. So let me pop that right here. This is the unshaded region, right? So this area here is 99% of the area under the T distribution. That area is 1%. Now listen, this shaded area that I drew is a lot bigger. And by the way, your templates didn't have this already pre-shaded. I pre-shaded it just to speed the process up when I'm working on this, for the purposes of the video. But your template is blank here, and you have to shade that region. All right, so let's go ahead and grab the t-score from the t-score table. So here's the t-score table. Right now, don't forget, if this were a z-score scenario, you would be grabbing the z-score from this little table here, which is in that PDF that I put up in week, I think it was 10, what distribution do I use. So this is for z-scores, but we don't have a z-score scenario. We have a t-score. All right, so we have to find the, go back over here, 1% alpha, 99 degrees of freedom. All right, so let me go to the table. Here's 1% alpha. Alpha equals 1%. Here's one tail versus two tail. Obviously, when you look at our picture, it's a one-tailed test on the right-hand side. So I'm going to follow straight down this stuff here. And if you're wondering, by the way, what are these percentages? These percentages over here, those are areas on the left. So for instance, when I look at that t-score right there, the area on the left of it is at 99%. So that's this T99. That's how you know what column to look down. So you got to look down. Notice the DF is right here, degrees of freedom. So you got to follow down to 99 degrees of freedom. You're like, wait a second. It doesn't have 99 degrees of freedom. It's got 80 or it's got 100. Now, obviously, most people would want to grab the one that's closest to, which is 100. In fact, you don't. When you're, statisticians like to play it safe. So it's probably a safer response to grab the one that's up higher on the table. So most people would grab the 2.37. So that's what I'm going to grab right there, 2.37. That's my t-score here, 2.37. Now, just for the record, rather than using this table, if you have your calculator, now this, unfortunately, this is only for a TI-84. So if you go to second distribution, and it's option number 4. Now, this is not in a TI-83, unfortunately. So it's option 4, INV-T. If I select INV-T, INV-T just looks up the t-score for you, so you have to go to the table. It needs area on the left, which was 0.99. It's the area on the left. And then it needs degrees of freedom, which is 99 degrees of freedom. So this looks a little weird because it's 0.99 and 99, but the reality is this is area on the left, which remember was 99% area, right? And then it needs degrees of freedom after that. All right, so you hit enter. Let it do its thing. And there you have it, 2.36. I grabbed 2.37. You can see it's 2.3646. You can see it's like it's so close in the middle. My math lab has allowances for that, so that doesn't hit you and mark you wrong for that, which is kind of fortunate. All right, so we got that. All right, so let's go ahead and keep filling this thing in here. The confidence interval we'll do later. The p-value is gotten from the calculator. So let's continue filling this out here. So remember, up top here, this little line that goes across and is this line that's vertical, which is the barrier between the critical region, which is right here, and the non-critical region. This is called your decision rule. And remember, you always write fail to reject H0 above the non-critical region. So this is fail to reject. And then above the critical region, that's the region where it's very unlikely for for a person to lie. So if someone lands out there, something weird is going on. So that's where you would say reject. So now that critical t-score, see that t sub c right there, that's his value that we just looked up in the table, 2.37. Let me pop that down there if I can. Yeah, I think I can do that. Yeah, okay, 2.37. All right, so there it is. In other words, this is 0 right here. And then that line that separates the critical region, the region that's very unlikely to land in, from the region that is likely to land in, that number is 2.37. So now remember, what happens? Well, what's going to happen is we're going to take the average that's known to be true right now, 2.86. We're going to compare that with the sample size and the average we have now for the sample, and then the standard deviation. This is going to create its own t-score, these numbers right here. Now, what's going to generate that? Well, that's called the testing statistic. So the testing statistic, notice, takes those bits and pieces of info, it's going to crunch its own t-score, and that t-score is going to land somewhere. Now, I have sorry about that. I have a an arrow pointing, right to this critical region here, but I don't know if it lands in there yet. It's just that this arrow here, I can move it anywhere from here, but this arrow is going to point in one of these two regions. So let's go ahead and I'm going to modify this formula. In other words, I'm going to grab the little bits and pieces and start plugging and chugging. So let's do that. All right, so I have to modify this. So it's x bar take off mu, which is 3.05. Take off 2.86 divided by the standard deviation, which is 0.66, divided by the square root of m, which is the square root of 100. Okay, so there's the numbers plugged in. Now, obviously, we've got to crunch this. Now, I'll show you in a little bit how you could crunch it in your calculator without, actually punching buttons. There's a way to just give the calculator this info and get the statistic out of it. Well, let's type it and get this number so we can pop it in there. 3.05 subtract 2.86, close the parentheses, divided by new parentheses, 0.66 divided by the square root of 100. All right, so let it go ahead and crunch that mess. All right, it's about 2.88. Now remember, my math lab will ask for this for a certain decimal place, so just be careful with that, round to whatever it says to. But you know what, for purposes of us right now doing this video, 2.88 is fine. So I'm going to grab that number and pop it in here. This is about 2.88. All right, so let me close this thing right here. All right, so there it is. Now 2.88. Let me move this over a little bit so it's kind of in line. Obviously, if this is 0, and that's 2.37, that's the critical t-score, this 2.88, that kind of lands out there somewhere. Now, we don't have to be perfect here. I'm just going to point it out there somewhere. In other words, 2.88 I know is landing past 2.37. So what's the point? The testing statistic is landing in the critical region. In other words, notice what the testing statistic does. It takes the x bar and it takes the mu. In other words, the x bar, which is the average from the 100 people that were sampled, compares it to the average that's known to be true. That's been true for a while. That's the average that the null is talking about. It subtracts them and finds how far apart they are. Notice this difference, you would expect it, according to the central limit theorem, to land close to the center. This one, not only does it not land close to center, it lands in a region that we know, according to the central limit theorem, which is almost impossible to happen. That 2.88 lands in the critical region. When that happens, notice what the decision rule says above it. Reject the null hypothesis. That's why we say the phrase reject above the critical region and fail to reject above the non-critical region. All right, so since the testing statistic lands in the critical region, we are going to reject the null hypothesis. So right over here, I'll write reject H0. All right, so now what? So now we have to come up with our conclusion. Now you may wonder right now, what about this p-value right here? What about the confidence interval? Let's worry about that in a few minutes. I'll show you how to generate all that stuff in the calculator. And remember, the p-value method is just an alternate way to do the test. This way we're doing right here is called the traditional method of hypothesis testing. Let's talk about how to word this final conclusion right now. Let's do that. All right, so the result of the test is reject the null hypothesis. So what I'm going to do is I'm going to come up here to the null hypothesis and write reject. So I'm going to highlight that. So I am rejecting that claim. All right, so obviously if you reject that claim, you're feeling pretty darn good about the next one. So I'm going to accept this one. And this is the alternative hypothesis. All right, so then we got to ask ourselves, what did we just accept? Well, we just accepted that the population mean mu is in fact greater than 2.86. All right, so in other words, this sociologist, her saying, hey, I think this is too low, actually looks like she's correct. So based on the given information, it appears that the population mean, in fact, is more than 2.86. Now, listen, we're not saying we know what the answer is. Notice this sociologist isn't claiming, hey, listen, I got the answer. I know what the answer is. No, she doesn't know what the answer is. She's just saying, listen, based on my evidence I have here, I feel that this average is incorrect. I feel, in fact, it is greater than 2.86. All right, so based on the given information, the population mean number of tweets is significantly greater than 2.86. The sociologist is correct. All right, so now this conclusion here, how do you word that and how do you come up with this conclusion, obviously? Well, I think the key is once you get the result of the hypothesis test, to number one, realize that's not the answer to the conclusion. That's just the result of the test. And remember, in this spot right here, we only say one of two things. Right here in the decision rule. Those are the only two things you're allowed to say in this spot. Either you reject this claim, the null, or you don't. You'll never say accept to this claim. We say the phrase fail to reject. You can accept this claim right here. You're not asking everyone in the population, gee, do you have a Twitter account? And two, how many tweets do you do per day? You don't have the ability to do that, so how on earth can you know what the actual answer is here? That's why we can never say accept for the null. We could either reject it or fail to reject it, and that's it. It's okay to say accept to the alternative, though. You could accept that it's to the right somewhere. That's what we just accepted here. We're not saying we know what it is. Notice this question nowhere says, hey, I got the answer for the mean. It's 5. Or the sociologist isn't saying it's 3.05. She's not saying that. She's just saying, listen, my sample of 100 generated an average of 3.05, which is too far away from your 2.86. I'm landing in the critical region. It can't possibly be that. All right, so there's your conclusion. Now, what else can we do here? What other things can we do? I guess, the one question I guess we could do is, how do I generate this testing statistic on the calculator without, this thing freezes sometimes, so I have to open it back up, without actually having to punch the buttons like that. It's kind of a little annoying that you have to do that sometimes. Let me show you where this menu is. So if you go to Stat, you move over to Tests. The first two tests right there, Z-test and T-test. Now, we just did a T-test, so you could use this T-testing menu. So it's option 2. I don't have data. If we had the raw data values, in other words, if we had those 100 data values, we could pop them in, L1. And the calculator would go ahead and, crunch the mean and standard deviation for us. We have the summarized stats. Let me move that over and hit enter. Notice how the inputs change when you do that. All right, so let's give it the info. mu0, that's H0, which is 2.86. X bar was 3.05. The sample standard deviation is 0.66. The number of samples was 100. And down here is where you select the alternative, as you can see. Ours was a greater than scenario, so it's the last one. You have to move it on top and hit enter. And notice how it switches. All right, and then you just go on top of calculate. So in other words, once you're convinced that all this information is entered correctly, you tell the thing to calculate. You can also tell it to draw, and it will draw the picture. I'm not a big fan of the draw menu, only because it draws this picture too accurately. And you'll notice that this area, you hardly see it. I'm not a big fan of the draw, and I don't usually use it. So I'm going to use calculate. So if I hit enter, notice the T statistic, 2.8787 ... That's what we got here, 2.88. So in other words, when we punched the buttons before, we didn't have to do that. The calculator will crunch that for us. All right, so you could grab this number, the testing statistic, and notice the calculator calls it a T, which is a T-score. Well, why? Well, this right here, the critical value, is a T-score. So what's that 2.88? Well, since it lives right here, it's also a T-score. It's just that it's a testing statistic that we use for T. This is called the critical value. That's a T. But all the numbers down here on this horizontal axis, they're all T values. And we're comparing T values. So the calculator calls this a T. And if you would have used the Z test, it would call it a Z. All right, so another thing we should consider is the p-value. Notice the p-value for this test, p equals 0.002 approximately. So I'm going to go over here. It says p-value. So this is 0.002. Now, if you read the information on the p-value methodology, it's just a different methodology, a different way to do the question. one that's different than testing statistics and critical values. So if you remember correctly, the p-value method, how you use it, it's a comparison with the alpha level. So you compare the p-value to alpha, and if the p-value is smaller than alpha, you reject the null hypothesis. If the p-value is bigger than alpha, then you fail to reject the null hypothesis. So this p-value is less than alpha equals 0.01. So p-value is less than alpha equals 0.01. So therefore, reject H sub 0. So this methodology here is just a different way to do the question. It's called the p-value methodology. Obviously, it's so much easier. I mean, think about it. You get this one number called the p-value, and if that p-value is smaller than alpha, reject. If that p-value is bigger than alpha, fail to reject. It's a much simpler process. But, you know, you don't fully understand that p-value method unless you really understand the traditional method. All right, so I think, hopefully this helps you out a little bit. I've had a handful of students, number one, say I can't find the videos, and I don't know why the videos aren't showing up, so I just had to create a different, I created pencasts at first, and the pencasts aren't showing up for students. So I decided to make a screencast instead, and hopefully this helps you out a little bit. I'm going to create another one of these for the population proportion P. That should help you out. All right, so if you have any questions, shoot me an email. Thanks for watching.